Okay, let's start looking at another test. This one's called the integral test. And by its name, you'll see that we're going to actually have to use an integral of some sort. Like all tests, it needs to satisfy some sort of condition, right? In the geometric series, we had to have some sort of form of a times r to the power of n, or a times r to the power of n minus 1. And with that, we can apply the geometric series test to find if it converges or diverges. So this one is very similar. What I want to do is start with a sequence defined as a sub n, right? And let's actually redefine it as a function of n. So, for example, if I were to have a linear function 1, 2, 3, 4, 5, or x0, like this, the function that pretty much maps exactly is just x, right? For x is 0, 1, 2, 3, 4, 5. But the thing about the function is that it's going to take every value in between, but as long as it hits these values along the way, that's fine. So that's the idea of redefining it as a function. And the function must fulfill 3 requirements. So the function, whatever function it is, the function f of x, has to have 3 things. So these are the important ones. 1, it's continuous, the function that you redefined it as. 2, it must always be positive no matter what. It can never dip down to the negative y-axis, or it can never have a negative value at all. And 3, it must always be decreasing, which is kind of a weird condition, because if it's always positive and decreasing, how does it not end up in the negatives as we go into infinity? Well, we can have functions that look something like this, where it doesn't go to 0, but it's still decreasing, even if it's by a small amount, almost like an asymptote. So these are the kind of types of, sequences or series we could look at. Something that kind of approaches something, but doesn't quite get there. Continuous, positive, decreasing. And now I'm going to show you how the integral test fits with these conditions with, a proof. But it's not really a proof, it's more like a sketch. So we can consider any random function that has this property, continuous, positive, decreasing. Let's just choose 1 over x squared. So the series that I'm analyzing, let me write it like this. The series I want to analyze is this. The infinite series as it goes, what is it? It's 1 over n to the power, it is, n squared. This is the infinite series we're looking at. And the question is converge, diverge, right? Always that question. It fulfills these 3 requirements. So what does the integral test say? Well, I can't really say it unless I show it to you with a picture. Let's say this is what the function looks like. Probably a bad picture. Probably something like this. A little bit better. I want to take a right Riemann sum. And what that means is I'm just going to start taking rectangles starting from n equals 1, right? And then move on. And you'll see that since these values or these widths right here are 1, the height or the value of if you plug it in is basically going to be that. So it's going to be, so this is x equals 1, 2, 3, 4, 5. Each has a width of 1 but a height of something else, right? I'm going to write the first couple terms. It's going to be 1 plus, let's see, if I plug in 2, it's going to be 1 over 4, and then 1 over 9, right? It's going to basically have the same value, or the rectangle has the same value as what it would be in the term, and then we just continue this process off to infinity, right? But then how does the integral, tie into this. Notice that because we took the right Riemann sum, this curve will always be greater than or equal to the sequence or these terms, the values of these terms, right? It's going to be equal to, or since there's like some parts that are less, if we were to sum all these rectangles, it is going to be always less than the integral or the area under this curve because there's missing area right here. And that's because it fits these qualities. Because it's decreasing, it's always going to have this thing. Since it's always positive, we don't have to worry about negative things. And if it's continuous, it allows us to take the integral of it. So, what does the integral test say? I'm going to keep this picture right here. What does the integral test say? Integral test. It says, given, let me write it in, I guess purple's fine. Given that it satisfies the three conditions, since the area under the curve is always greater, we can kind of apply the comparison test in a way, like a comparison test, that since it's always greater, if the integral converges, then the infinite series must converge. So it has to fulfill the three conditions, but then, since it's bigger, so we can say the integral, or let's say three conditions met. Let's see how I want to phrase this. We have this infinite series starting with any number, I'm just going to give it capital N, all the way to infinity of any type of, I guess, series that has the three condition, right? This has to fulfill that three condition property. If that this will converge if that integral from whatever that number is to infinity of, I guess, the function that kind of maps that, well, if this converges. Since no matter what, this integral will always be bigger than or equal to the sum. I guess the other one would be, it would diverge if the integral diverges, right? Or this would diverge if the integral diverges. And it allows us to say that as well. So this is the first part. The second part is this will diverge if this integral diverges. So that's the idea of the integral test. Basically, we have to fulfill these. It has to be this. There's no exceptions at all. It has to do this. And since the integral, the true area under the curve, is always going to be greater than the, I guess, the sum of the rectangles because of these missing area pieces. Since it's bounded by, is what we call it, if the area converges to a number, the series must converge into a number. And in the opposite, if the area diverges, then the series must also diverge. And that's the idea of the integral test. Hopefully this picture made sense and this explanation made sense, because it's a very interesting test. If I were just to give you a definition, it would be very confusing, because it's like, oh, we got a series and we got an integral, but how do they tie into each other? They tie into each other through this diagram. Since this quality holds, we are allowed to do this. And that's it for this video.